Alright, so today we are starting chapter 11 in our book, which is on space figures and cross-sections. We're going to be dealing quite a bit with three-dimensional figures, including surface area, volume, things of that sort in this chapter. But we're starting off just kind of talking about some general stuff in terms of three-dimensional figures or space figures. So, little vocabulary to start off. It says a polyhedron is a three-dimensional figure whose surfaces are polygons. A three-dimensional figure whose surfaces are polygons. Each of those polygons is what we call a face. Okay, so each polygon on the polyhedron is called a face. When two faces meet or intersect, they form an edge. So that line that they meet at forms an edge, and I'll show you a visual of this in a second. And an edge connects to vertices. Now, it's common for you to hear someone say, oh, one vertice. Well, the singular for this is a vertex. Okay, so don't call it a vertice. It's plural vertices, singular vertex. Anyway, we're going to look at a couple pictures and see if we can identify these things. So, first of all, this top figure here, this top figure there, number one, first of all, is it a polyhedron? Well, it's a cube, or a rectangular prism at least. Each of the faces that we can see are polygons, so it would classify as a polyhedron, right? So it's a little happy face, it does work. Now, each of these surfaces would be called a face, so here's a face, and this is also a face here. Well, these two faces intersect at this line, which is called an edge. And then this line connects to points here. These are called the vertices. So you see how it kind of connects. Anyway, is this second figure here, is this a polyhedron? Well, do we have a bunch of polygons connected? Well, yeah, we have a triangle, 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 they're all triangles, and then a pentagon, it looks like, as the base, which means it's a bunch of polygons. Again, you can identify faces. We have triangle faces. We have a pentagon face at the bottom. The edges are the lines, and the vertices are the corners. Okay? These two, again, triangle, 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 right, all made of triangles there. So that would be considered a polyhedron, as would this one. We have, it looks like a 2, 4, 6, 7, a heptagon for each of the bases, and then rectangles on the outside, which means it is also a polyhedron. This picture here is a picture of multiple different types of polyhedron. There are, infinitely many that you can think of. So they don't all have to be the same shape, right? Some have triangles and quadrilaterals, some have parallelograms, some have pentagons, hexagons, all mixed and matched. Okay, so you'll see tons of these different pictures. Now let's look at this figure here, this cylinder right here. That cylinder, we want to see, first of all, is it a polyhedron? Well, are all of its faces or all of its surfaces, are they all polygons? Well, we have, if we look at the top here, the top of that shape would be a circle, and a circle is not a polygon, which means this would not be a polyhedron. So a cylinder, not a polyhedron. What about a sphere? Well, it's just all around. There aren't any different faces. It's all one kind of surface, right? So this, again, not composed of polygons, not a polyhedron. So they can't have a round surface. They need to all be flat. Okay? We're going to look at a couple of things as to what happens with these. So we're going to look at a couple different types of polyhedron. Now you can imagine a cube, and I could ask you, what are the number of faces on a cube? Right? Well, a cube is just your ordinary box, right? So it's going to have 6 faces. Well, you can also look at the number of vertices or the number of corners on that cube. And again, if you just look at a shoebox in your house, you'll notice that it has 8 corners. Right? 8 corners. Where the edges now, we're going to look at that. We have 4. So I'm going to, insert a picture of a cube here so you can kind of see what I'm talking about. So I have this cube here. We have how many? So again, when we're talking about the vertices, we have 4 corners there, 4 corners there. This one here you can't see; it's behind the cube, which gives us the 8. But if we're looking at the edges, we'd have 1, 2, 3, 4, 5, 6, 7, 8, 9 going down there, 10 going here, 11, and 12. We'd have 12 edges on that cube. And again, I highly recommend, if you don't remember or if you can't visualize what I just did, take out a shoebox. Take out a box of any kind. Just count. Let me then get rid of this picture here. So now we have a triangular pyramid. And what that means is that the base is a triangle, like so. So the base is a triangle, and then the pyramid connects a bunch of other triangles, so it looks like so. Well, how many faces do you see? Well, there's going to be 1 here, 1 here, and 1 in the back, so that's 3 faces, and then 1 on the bottom, which gives you 4 faces. How many vertices do you see? Well, we're just, again, counting the corners in this case, right? We're counting the corners, so we have 1 there, 1 there, 1 there, and 1 there, which is 4. And then we want to look at, excuse me, how many edges do we have? So if we're looking at how many edges, I'm going to trace those in green here. We have 1, 2, 3, 4, 5, and then don't forget the 1 in the back there. That would be 6. Okay? So it's kind of how we're piecing this together. You can try these next 2 on your own, see if you can fill those in for a rectangular pyramid and a hexagonal prism. I'm going to skip the rectangular pyramid for now and go to the hexagonal prism. The hexagonal prism, actually, I'll do both. So the rectangular pyramid, first of all, that just, again, your base is a rectangle, and then you're going to have a bunch of triangles formed there. So how many faces do you see? Well, there's 4 triangles up top, right? So 4 triangles plus your base. Don't forget your base. I forgot the base. 5 in total. How many vertices? Again, that's just looking at corners. Well, there's 4 corners at the bottom, 1 on top, which gives you 5. And if you're looking for the number of edges, again, you can verify this on your own. There would be 8 edges. What does a hexagonal prism look like? Well, it looks like a hexagon as one of your bases, beautifully drawn, of course, and that connects to another hexagon, like so. So this line here, this line coming across here. So all of your bases, basically, going to be... that was a terrible picture of a hexagonal prism. You have 2 hexagons that are connected, basically. And since we're already going behind on time, I'm not going to fill that one in. So I encourage you to recommend that one. You look at that one on your own. If you really can't draw it, just Google image hexagonal prism, and you'll see exactly what I'm talking about. In general, though, there's this thing called Euler's formula. Euler's formula. It says that the number of faces plus the number of vertices is the number of edges plus 2. So F plus V equals E plus 2. So let's see if that's true in the chart we just made. Well, again, let's look here. We have F plus V, that's 6 plus 8, which is 14. Hey, that's 2 more than 12, right? We have 4 plus 4, which is 8. Excuse me. Hey, that's 2 more than 6. We have 5 plus 5, which is 10, and hey, that's 2 more than 8. So that's kind of where that pattern comes from. Okay, so I can ask you a couple questions on this. I could say, for example, that a polyhedron has 5 faces, 1 rectangle, and 4 triangles. Find the number of vertices. Well, you can kind of struggle with this as much as you want to try to draw it in 3 dimensions. So there's another strategy, and that would be to draw what's called the net. Okay? What that means is if you were to unfold the shape, or the polyhedron, it would look something like this. I'm going to estimate what it will look like. If I have a rectangle, right, and it's connected to 4 triangles, I'm going to say that there's going to be a triangle on each of these sides here. So imagine that these folded up and these triangles all connected, and it would end up looking something like this. Something, I can't find anything now. Okay, something like this. If I were to fold that up, the triangles would connect up top. It would look something like that. Now, I'm going to look at a different circumstance in case you wouldn't have drawn it that way. We're going to look at that in a second. But how many faces are there? Well, again, that's just looking at that's just looking at how many polygons you see. 1, 2, 3, 4, 5. Right? It says up here there's 5 faces. So F is, again, let's write Euler's formula. F plus V equals E plus 2. So F is 5. We don't know V. Well, do we know E? Well, again, let's just count the number of lines. Let's look over here first. So we have 1. Let's see if we're going to get this right. 2, 3, 4, 5, 6, 7, 8. So we should have 8. Well, if we count these, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So how does that make sense? We have 12 there. Well, if you think about it, when these fold up, these here, let me match some for you. These 2 edges here would connect when they fold to form one of these lines. Right? Similarly, these 2 edges here would connect to form, let's say, this line here. Does that make sense? So you're looking at these 2 edges here, connecting to form that purple line. They're connecting there, which means really if you count this, you can't necessarily say that there's 12 edges there. Okay? You can't necessarily say there's 12 edges when in reality there's only 8. Okay? So there's a couple different strategies there. Anyway, so it has 8 plus 2, right? So we would say the number of vertices is 5. Because you just solve this equation, right? 5 plus something equals 10. Therefore, that something is 5. Anyway, so that's kind of how you use Euler's formula. I'm going to stop there. And the next one is going to be on what's called cross sections. Should be a short part 2. So that's it for now. I recommend you try some problems on your own. And I'll see you in class. Look at part 2.